All right, last one. Means I can go on for a couple hours, right? No one's after me. Well, anyways, it's a pleasure being here. I'd like to thank the organizers of the workshop for inviting us. My name is Bruce Davis, and I'm with a company called Rocore, based in Louisville, Colorado. And today I'd like to talk to you about some work we're doing in conjunction with JPL. In fact, we're under contract with JPL to help develop an external occulter for a planet finding mission. So before I get into the details of the occulter itself, I just wanted to give you an overview of what we do at Rocore, who we are. We're a company based out of Louisville, Colorado, which is just outside of Boulder. And we have about 10 people working full-time in our group. About 6 of them are engineers and the rest are support. And our main mission is to reduce asset cost of spacecraft systems during launch. And how are the petals itself going to interfere with or interact with each other in terms of how are they going to vibrate? How are they going to be preloaded against each other and against the ring itself, the truss or the preload positions around the center. So what we've come up with in conjunction with JPL is a series of connection points. Let me look over here; it's more clear. Connection points to understand and identify how those petals come together, and to identify the different ways in which the system can be preloaded. So one method was, do we have an external belt that contracts radially around the outside that we unwind during a deployment scheme, or do we have a series of connection points on the inside that release one at a time, which would involve a significant number of release devices. This just give you a taste of some of the configurations that we've been doing our structural analysis with. You can see here's a few pictures of the mode shapes of the system, and I have 2 different ones in here. One in which the edges of the petals are deflecting, and toward the center you can see on the right you can see the center is deflecting a lot. So if there's anything to take away from what we're doing when it comes to an analysis standpoint, is that we are looking at the system in multiple configurations in which you can restrain it from the center with an outside band, or restrain it from the center on the inside, and to understand exactly how these petals are going to react during launch and then during initial on-orbit transfers and things like that. In addition, there's a lot of effort to characterize those blankets and how that foam interaction from one petal to another is actually going to transfer loads and probably even more importantly induce damping within the system, which would have a dramatic effect on the natural frequency. I'll get into a discussion on exactly how is this thing going to be deployed. And we've been working with JPL for about 2 years now, coming up with different concepts. Both a controlled type of deployment and then a less controlled type of deployment where there'd be some dynamic motion. And just to get an idea, we did an early study where we did a dynamic model, which you basically take a single petal by itself, and then just release it and see what would happen. And we found that there was a fairly large amount of velocity at the tip, and it was also what you could probably consider a level of chaos within the tip, in which once you have a whole series of petals interacting with each other, because imagine if you can't release one petal because they're all furled together, but imagine releasing multiple petals at the same time and the tips are all moving. So if you have one hinge point between the petal and the ring truss, if that has a little bit more damping, then you're going to get a non-symmetric deployment, and then the tips are going to interact with each other, and as I said before, they're optical surfaces. There's a lot of concern there. So because of this initial study, the baseline approach has evolved to be a controlled deployment, but there's various types of controlled deployments. One is one that releases the tips of the petal sequentially around the ring, which is one direction that we're pursuing, and another one which we have a band that completely locks in the exterior of the system and very slowly and with a lot of control releases the segments of the petal part by part. Let's see here. I think I have 2 more slides. Oh, no, I'm sorry. I have to talk about some of the work we're doing actually at Rocore itself. So we have several petals that were fabricated at our facility now. We have a a full-scale truss structure that we've built. You can see here, as well as, so we have this structure here that's circular that represents the diameter of the hub itself. We can see we have a pedal on there that wraps around the hub, and then we have a series of, only one show, but we have a series of offloaders that allow us to reduce the effects of gravity on the system. So you can take a look at this concept, and then I keep pressing the button. Okay, then here's our facility itself. You can see these pedals. We have 3 of them, and we've been doing a series of tests to validate our models, but also to identify upcoming issues that need to be resolved, such as impact from one to another. So this has been a lot of fun to work with. These pedals are enormous. This is only a half-scale pedal on a full-scale hub, so it's amazing. We're going to be fabricating larger pedals soon to get to wrap all the way around. They go about 120, I think 270 degrees around the whole system, which is a very large deployable structure to be working with in a lab. And then here's some other pictures of some of the interfaces that we're starting to work on. We have a design for a snubber stack. And this, as I mentioned before, snubbers are the kinematic mounts that hold one pedal with respect to another pedal. That way they can be restrained during launch. You can see on the left side is some of the CAD coming from the vertical, looking down straight, and there's a lot of foam in there, which is why you don't see any gapping between them. But yeah, we have that green cylinder that represents a mechanism we're developing to release these pedals part by part. All right, let's see. I can see better over here. So the other thing that we're doing outside of the high-strength composites is we're actually working on the spokes themselves, which are the wires that connect the ring truss to the hub. JPL needed a group that could design a system that had a very linear strain with respect to a low loading. And we took on that challenge, and we developed a preliminary demo spoke, as we called it, that was metallic this summer for their half-scale truss. And we're closing in on some funding that will develop a full composite system for a flight demo that would be performed, well, not a flight demo, but a full demo system that would be formed in about 1.5 years to 2 years. Oops. So in closing, I'll just go over, just give you a roadmap of where we are at, and some of this is kind of focused on our funding and where that's come from, and can give you an idea for where we're going. So our original contact with JPL started off with a phase 1 SBIR, and that initiated some of the first concepts for how we would furl and unfurl the pedals. And that went well enough that we received a phase 2, and that was enabled us to build our hardware and start really getting into the details of this stowed analysis and that finite element analysis system. We're getting ramped up. We're going to be working with JPL in the near future to build a half-scale unit, a half-scale system that is complete in its entirety. So I believe on that previous slide, I'll just go back to that previous slide. I didn't mention that. There was a picture of this truss. So you can see that ring and that center hub is all performed at JPL. It was a phenomenal work of engineering that they did there. And then after it, part of that deployment was contained 4 pedals, which didn't have any furling capability. They were just kind of rigidly attached. So when I mentioned that we're going to be working with a half-scale system, we're going to essentially take this ring truss and we're going to do full furling with it, is on the game, as the current game plan. And then, as I mentioned before, we worked on, did some initial work with JPL on the metallic spokes, and we're getting excited to ramp up with some composite spokes that we have some funding things in the works to see if we can start that fairly soon in the next couple months or so. So with that, I went through it pretty quickly, but I just wanted to give you a taste of what we're doing at Rocore. We're really excited to be working with JPL, and as well as this community being here and learning what you guys are doing. It's been a pleasure. So if there's any questions, I'll take them now.
Can you speak a little bit about how you're getting the near zero CTE? Is this purely a materials approach?
Yes. So there's you can actually acquire a lot of fiber materials have a negative CTE, and then you can actually offset that with other materials that have a positive. On top of that, there's a level of influence that the resin itself has on the structure, because that usually has a fairly high positive coefficient of thermal expansion. So it's really a matter of just playing with the properties and playing with the curing of the composite too, and testing to get that. But it's been fairly well known within high-end composite companies that they can perform near zero CTE structures. So, go ahead.
So that was the first time that I've seen a dynamic model of the unfurling of the petal. I'm not really surprised it's chaotic looking. I was wondering if you actually accounted for in that model that the hub isn't itself inertially fixed. Because something I've always been a little worried about is, as you unfurl, is that going to destabilize the spacecraft in any way?
Yeah, that's a great question, and I'll have to put out a disclaimer that I didn't do that model myself, but and I try not to use the word chaotic because that has certain implications. But the reality is it's an extremely complex system, and there's so many factors that go into play, especially the one that you brought up that I didn't, that it's free floating. So there could be some effects there, and you have 28 petals, 28 independent systems, surely, and tips that are extremely flexible. There's surely going to be some contact that's not characterizable up there, and there's no way to test it on the ground either. Because so thanks for your comments. I hope I answered it in its fullness. But
yeah,
thank you. Go ahead.
What's the longest boom we can make out of this?
What's the longest boom we can make? That's a good question. It's as long as our oven is in-house, but we can find vendors without difficulty to fabricate a boom that's very long. I know that I bet someone in here knows how long the booms are on. Actually, I'm not sure if JVST has composite or not, but come to us and we'll let you know. I don't know offhand exactly what the longest boom that I've seen in literature, but I know that. Excuse me? We've done them over 100 feet. Yeah. The longest we've done to date, I believe, is about 4.5 meters in-house. But yeah, I mean, they can. Another thing too is you can splice booms together. That's been done multiple times as well. So theoretically, it's as long as you need, as long as your application, as long as they can structurally handle it too, because there is a function of stiffness as you get farther away from the root. So, all right. Well, thank you.